Hello, calculus students. I've left my nice microphone at school, so unfortunately you're going to have to deal with my laptop microphone. I thought we'd do this problem from the study sheet. Let's read through it and do it together. So we've got this function. It says find f prime and use it to find all local and global extreme values. Use it to determine where f is increasing and decreasing. Find f double prime and use it to find points of inflection. And then put together all of that information and give a nice sketch of the graph. All right. So we'll start with f. I just want to observe where are features that we know about this already. So it looks like f has a 0 when x is 0. It does not have any vertical asymptotes because the denominator here can never be 0. It has a horizontal asymptote at x equals 1 because if we imagine the limit as x goes to infinity or negative infinity, this will simplify to be 1. All right, so we know that stuff already. Let's find f prime. I think that I will use the quotient rule here. You could try and rewrite this as x squared plus 3 to the negative 1 and then use the product rule. It doesn't seem obvious to me that that's going to be any cleaner. So quotient rule, low times the derivative of high minus high times the derivative of low. And I will square the bottom. And there I am. All right, let's go ahead and simplify. So when I distribute this, I will get, when I distribute in green, I will get 2x cubed plus 6x. And this is minus, this is a 2x and an x squared, so 2x cubed. Therefore, these guys cancel. So my simplified function will be, I lost it. Okay, 6x over x squared plus 3 squared. Great. Where are the critical values of this f prime function? Remember, critical values are whenever the function is 0 or not defined. This function is defined everywhere because it's impossible for this denominator to be 0. And it looks like it will have a 0 when x is 0. So that's the only critical value. Let's go ahead, rather than answering these in order, as long as I'm finding derivatives, let's find f double prime, and then we can come back and answer all the questions. So f double prime, I'll use the quotient rule on this guy. So I've got low, d high, minus high, d low, and then here I need to use the chain rule. So I brought the 2 down, and that's become 1, and now I've got to multiply by the derivative of the inside, which is 2x. And then I'll square the bottom, and all as well. Let's simplify this numerator. So what I'm noticing is I've got this term happening as a subterm of both terms at the top, so I'm going to factor that out to start with. So I'll take one of these out, and I'll take one of these 2 ones out, and I'm going to cancel that with one of the ones on the bottom. Oh, sorry, this should be to the 4th power. So I'm going to cancel this and one of those with that in the bottom, so this will actually become to the 3rd power. All right, so far so good. So now we've got I'll distribute this, so we've got 6x squared plus 18. And now that this is gone, I've got, let's see, 6 and 2 and 2, which is 24. And I've got 2 x's, so minus 24x squared divided by x squared plus 3 cubed. And when I cancel these, that gives me 18 minus 18x squared. So 18 minus 18x squared over all that stuff cubed. All right, let's go back now that we've got all this stuff and figure out what the questions are asking. So question number 1, Find f prime and use it to find all local and global extreme values. All right. So extreme values, let's sketch this. Extreme values are only going to happen where f prime, the critical values of f prime. So, local maxima could happen either where f prime is 0, in which case there would be a horizontal tangent, or for some curves, if f prime were not defined, there could be a corner or a cusp there, but that could also count as a local or global maximum. We decided that the only critical value of f prime was at x equals 0. So in order to test what type of extreme value this is, if it's a maximum or a minimum, we need to look, is the curve is it going from increasing to decreasing, or is it going from decreasing to increasing? So I've got a test on either side of 0. So here's 0. Here's values for f prime. And it only matters if f prime is positive or negative for whether f is going to be increasing or decreasing. A second thing to notice is that this denominator is always positive. So what that means is that when x is less than 0, I've got a negative number in the numerator divided by a positive number, so overall f prime is negative, which means that f should be decreasing on that interval. And when x is larger than 0, I've got a positive number over a positive number, which means f prime is positive, which means f should be increasing in that interval. So that tells me that at x equals 0, I've got a local minimum. Because that's the only critical value, I know that the f function is increasing on the interval from 0 to infinity. So that minimum is not only a local minimum, it's a global minimum, because it's the only minimum that's there. So if I'm going to answer the original question, find all local and global extreme values. All right, so I would say there's a local minimum at x equals 0. It is also the global minimum. All right, B. So let's look at where f is increasing and decreasing. All right, great, we've already done that. F is increasing on the interval from negative infinity to 0, and f is decreasing on the interval from 0 to infinity. Was that right? Oops, sorry, I got that backwards. Okay, well, it's too small to write, but decreasing and increasing. Cool, so only one more left. Find all points of inflection. All right, so points of inflection happen when the second derivative changes signs. So let's look and see what that happens. This is the second derivative. And it's only going to change signs at a critical value, so either where it's 0 or not defined. Again, this is defined everywhere. So the only critical value of f double prime is when the numerator equals 0. Which is going to happen when x squared equals 1 or x is plus or minus 1. So those are the two values we have to look at. So let's test them. Here's -1, there's +1. All right. Let's again notice that this denominator is always positive because no matter what x is, I square it, making it positive, and then I add 3, so it's positive, and I cube it, so it's positive. So in terms of knowing what sign f double prime is, I can ignore the denominator. All right, so let's choose a value that is inside each of these intervals. I'll choose maybe -10. So when x is -10, this is a very large positive value. So I've got 18 minus something really big is going to be negative. So f double prime is negative, which means that f is concave down. All right, let's choose 0 for this middle interval. So when x is 0, this is positive, which means f is concave up. All right, let's choose something in this interval. We'll choose 10 again. And that's the same thing as negative 10. So I've got 18 minus some very large positive term. So that's going to be f double prime is negative, which means we are now concave down again. So that means I've got points of inflection both at -1 and at +1. Because the curve is going from concave down to concave up, or vice versa. Okay, let's put all of these things together. Here we are, we're drawing a graph. So I'll add some axes. Reviewing the things I know already, I know it's got a 0 at x equals 0. And I know that that is a, I've drawn this badly. I should have moved my axes down. I thought it was a global maximum. Now I'm looking at a global minimum. That's okay. I know that, well, let's choose some spacing here so that it looks good. So here's -1, there's +1. All right, so I know in this interval, my function should be, I'm looking back at my work, I know it should be decreasing, and I know on this interval it should be increasing. I know in this interval it should be concave down, then concave up, then concave down again. All right, so let's see. Decreasing concave down looks like this. And then here's my point of inflection, and now it's concave up, giving me a 0 tangent here, still concave up. And now I'm transitioning to concave down. And there was an asymptote at 1. I'm not actually touching the asymptote here, I'm approaching the asymptote. All right, so let's see, does this make sense? I'm double checking all the things. Is it decreasing on that interval? Yes. Is it increasing on this interval? Yes. It has a local minimum there. Yes. It is concave down here, inflection point, concave up, inflection point, concave down. All right, I think we've done it. Let's just check in Desmos to see how we did. And here we are in Desmos, and that looks pretty good.